All right, so here we go for a lesson on antiderivatives. And keep in mind this anti means that we are doing the opposite of taking the derivatives. And that, of course, is what we know as finding the integrals. So the derivatives and your integrals are opposites. Keep that in mind. And we talked about a couple other opposite operations. We talked about how multiplication and division are inverses. Of course, addition and subtraction are inverses. If you have your something squared and the square root, those are going to be inverse operations. And of course, my favorite, if you remember when we talk about that sweet little student of mine that had a good time trying to figure out where the end was between the FOILing and factoring loop. So do you remember when I told her that like x, I don't know, we'll make it up, x plus 3 and x minus 3, and she did x squared plus 3x minus 3x minus 9, x squared minus 9, and then she went right away into, oh, I know how to factor that, x plus 3 and x minus 3. And then she's like, oh, wait, I can multiply. And she ended up in that FOILing and factoring loop. So that can happen to us again today when we talk about finding the derivative, which is this dx symbol, and finding the integral, which we now know is this summation curly QS symbol. All right, let's jump in. First of all, we're going to be asked to find the derivative. So here we go. If I find the derivative, I know that f prime of x is equal to my exponent comes down as a factor times my x to the 1 less power. And of course, you know that the derivative of that constant is 0. So I don't really need this 1 here, and I don't need that 0, but I still put them there because I want to make sure you remember that that's what we do. All right, we'll do it again. F prime of x is equal to, my exponent comes down as a factor. There's my x to the 1 less power. Derivative of negative 5 is 0. Huh, that sounds familiar. All right, let's try it again. F prime of x is equal to, my exponent comes down as a factor times my x to the 1 less power, and then the derivative of a constant is 0. So check it out. Each of these problems are different original functions, and I can keep in mind that each of these are my different original functions, and each of these are my derivatives. But the interesting thing is the original functions are not the same, but the derivatives are. So if you were to ask me which original function has a derivative of 2x, I couldn't pick one of them because they all have that same derivative, but they are not the same function. And this is where we're going to remember to kind of cover ourselves, to recognize that we may have lost a constant along the way, and we're going to be reminding each other to add a plus c to everything that we do. More about that in a minute. All right, so this is the antiderivative or the integral of 2x. The derivative and the integral are inverses. So we're again going to be talking about this idea of here's our original function, and all these different names apply: accumulation, area under the curve, antiderivative, and integral. Just the same as when I talk about my x-intercepts on a graph, I can refer to them as my zeros, I can call them my roots, and I call them my solutions. Same idea, each of these is a way of referencing our original function. My rate function is going to be my derivative. So if I call it my derivative, my instantaneous rate of change, the slope of my tangent line, each of those represents a different rate. I find my rate by taking the derivative. So taking the derivative is what we've been doing by finding that rate of change with respect to x, d dx. So then today's lesson is about us working backwards, and we're going to start taking the integral. So when we come up and finding the integral, as a reminder, it's that cute little curve. And we have that lower boundary, we have that upper boundary. And that whole conversation came from finding the limit as the change in x approaches 0 of that summation on some boundary from a to b of my original or of my rate function. So taking the integral takes us up, taking the derivative takes us down. And just like my sweet little friend had an infinite do loop between FOILing and factoring, you can take the derivative, find the integral, take the derivative, find the integral, and go back and forth like that. All right. It helps us if we look at things in comparison. So as a review, your power rule for your derivative, let's go ahead and say that I have my original function of x cubed. So let's say that I have x cubed. You know that when you're looking for the derivative, you're going to go ahead and find d dx of x cubed. And your method for doing that is bring the exponent down as a factor times your variable to the 1 less power. So let's talk about what you just did. You're going to multiply by your exponent, and you subtracted, I'll get rid of the ed, you subtract 1 from your exponent. That's that process of using the power rule to find the derivatives. Well, now when it's time to do the inverse, we're going to talk about finding the integral. So we're going to start with 3x squared, and then we're going to move in to finding that integral. All right, so what we're looking to do is to find the integral of 3x squared, this area under the curve. And what that looks like is going to be an inverse conversation from what we did here. So instead of subtracting 1 from the exponent, our first step is going to be to add 1 to the exponent. So I'm going to build this box here. I'm going to show my box here, and I'm going to build my integral inside of it. So I'm going to take my value here, and this 3 travels along. Here's my x as a variable, but when I add 1 to the exponent, that's going to be now a 3. Instead of multiplying by the exponent, now I need to divide by the exponent. So here we have, divide by 3. And our last conversation that we need to remember is we need to account for whether or not there was a constant in my original function. And we need to remember that plus c because of this conversation up here. How do I know which is my original function? I'm going to have to do some more math to figure out what that constant was that I lost when I took the derivative. Now that I'm doing the opposite of taking the derivative, I need to remember to account for that plus c. By the way, let's have a chat about what we can use as a check. Do you remember in Algebra 1 where we made you check all of your equations and your solutions. All right, so if I say this was my original function, when I go ahead and I look at that, now you and I both know that that is where I started over here, but but I'm going to check my integration by doing the opposite, which is finding the derivative. So I'm going to go ahead and find the derivative of this, which is going to be 3x to the 1 less power. So because this derivative value checks over there, I know that I did my work right. This plus c, of course, is going to go to that 0. So I don't need to worry about when I take the derivative of c, it is going to be 0. So I ended up with my original. Everything's fine. All right. So when we look at these examples, you really, really want to stretch your brain, and you really want to think about thinking backwards. Let's talk about what we have here. This is some kind of rate, and this symbol is asking me to go ahead and find the area under that curve. And remember, that was the sum of all of my little rectangles that I had. And part of that rectangles, my length times width, remember, this is going to be that height that I have, and this dx is going to be that width of all my little rectangles as I go. So this summation is asking me, can you take me back to my original function? That's code. Take me back to my original function. So what I'm going to do is I'm going to take my x, I'm going to add 1 to the exponent. If I have 1 here, now I have 2. And I'm going to divide by that exponent. And if I want to check, I can go ahead and take the derivative of that value that I got. So 2 times x to the 1 less power divided by 2. Of course, these cancel out. And yes, I ended up with what I started. So the integral, my original function, was a quadratic. My rate of change is linear. I was given my rate, and I'm going up to my original. All right, let's talk about this. I want to find the formula for the area under the curve. So I'm going to go ahead and think backwards. Here's my x to the 1 more power, and I'm going to divide by that exponent. If I want to check it, all I need to do is find the derivative of what I say is my original function, and my 3 comes down, x squared to the 1 less power, and then of course I can cancel, and I end up with that as my derivative. All right, let's hop over to the back. All right, so now we've got something with a little bit of more meat on the bones, but I want you to keep in mind you're undoing the power rule. This is asking you for the area under the curve. That's asking you for the original function. And when I see this dx, that reminds me that what I'm given is already a rate. So I need to go back up to my position or my original function. All right, so when I take the integral, and remember this 3x tags along. So I have 3 and x, and I'm going to increase my exponent by 1, and I'm going to divide by that exponent. Minus, here's my x, and I'm going to increase my exponent by 1 and divide by that new exponent. Now this is tricky here because what I want you to think about is this 1 has an x to the 0 as its variable. So when I take x to the 1 greater power, and I have that 1 as a coefficient, and I divide by that 1. So what I need to remember is, now it's time for me, I can simplify. So these 3's cancel out, and I have x to the 3rd power, x cubed, minus x over 2 squared, and then this becomes just simply plus x. Now the most important thing is we need to remember our plus c, because there might have been a constant here that I lost when I took the derivative. In fact, now that we mention it, we need to come back to that front of the page and add our plus c's. So make sure that you include that plus c. And that's going to be the thing that we need to help each other remember more than anything else. All right, back again on the back. I wanted to make sure we added those plus c's. We are taking the integral, which means this is my rate, and I want to go back to my original function. So the interesting thing that we can do here is just like when we did for derivatives, if it's easier for you to rewrite this function like this, then that can help you manage the rules a little bit easier. All right, so here is my x, and I'm going to take it to the 1 more power. Whoop, did I get you there? Divide by the new exponent and your plus c. So if we want to rewrite this, we know that this is the opposite of 1 over x plus c. That was our original function for this rate. All right, so kind of tying it all together, we want to make sure that we know that we're going back to, we did not include upper and lower limits. So the integrals that we've been working on so far, when we calculated all those areas, we had some kind of A to B boundary. We knew that we had some area that we wanted to. Those are called definite integrals. What we're working on today is coming up with generic rules, general rules, that can be applied to any rate situation. So we're just going to be practicing some of these generic rules, and then we're going to go back and start doing some definite integrals where we have upper and lower limits. So indefinite integrals, no upper and lower limits. So instead of calculating the area under the curve for a set boundary, we're calculating the area under the entire curve. And then once somebody gives me a boundary, we're going to start applying that. All right, so let's take this next example, because what we're looking here is some kind of multiplication. If we're taking the derivative of this, we'd be like, wait, that's the product rule. And we remember that that got pretty complicated when we had to do 1 times the derivative of the other plus the other times the derivative of, and then we can be like, oh wait, maybe we can simplify this expression first. So as I'm finding my integral, my area under the curve, I'm realizing, you know what, it might be easier to take this expression and call it 4x cubed plus 2x squared plus 1x dx. Because then finding that rate is going to be a whole lot easier. Remember, they're indefinite integrals. We don't have an upper or lower boundary. So what we're doing is we're coming up with a general rule that we can apply when we are given that boundary. So here we go. Let's take this first term, and this 4 comes along for the ride. so don't forget about him. My exponent goes up one more, and I'm dividing by the exponent. This 2 comes along for the ride. My exponent goes up 1, and then I'm dividing by my new exponent. No coefficient here, so I'm going to go to the 1 more, divide by that new exponent, and then of course don't forget your plus c. Now if I can simplify, I will. So these 4's will cancel out. X to the 4th plus 2/3 x cubed plus, whether you call this 1/2 x squared or x squared over 2, doesn't matter. But then don't forget your plus c as your final value. This is my original function that gave me this rate. This symbol asks me to go from the rate back to the original function. All right, so that is our rule for our inverse of the power rule. So now we're going to go ahead and talk about a couple other rules that we can understand and use often enough that we memorize. So if we have exponential integrals, you remember this value, Euler's number, and we love taking the derivative of e to the x because the derivative of e to the x is e to the x. So what we have to ask ourselves is which function gives us this derivative. So my original function that gives me a derivative of e to the x, yep, is e to the x. Don't forget your plus c. All right, the integral of a to the x, Let's talk about that. So let's think about if I wanted to find the derivative of an exponential function. So I know that the derivative of a to the x is going to be a to the x times the natural log of a. But as I'm working on that, this part here is missing. So where is it? Well, it must have canceled out. So when I go to take the derivative of a to the x, or the integral of a to the x, I'm going to have a to the x over the natural log of a. And then don't forget your plus c. So keep in mind something about the natural log of a. That's asking you what exponent on e gives you whatever a represents, whatever constant. So this constant value is just one that eventually is going to mathematically either cancel out or fold into our value. So this has a definite value. There's no variable as a part of that. So it's one of those thinking backwards things that helps us figure out that we end up eventually memorizing. All right, let's go over and talk about our logarithmic integrals. And I kind of gave the answer to this one away by having this title, but when we talk about my logarithmic, if I were to take the natural log of x, if I were to take the derivative, doesn't that give me 1 over x dx? So now I know that if I'm taking the integral of 1 over x, that takes me back to my natural log of x original function. So an interesting question that some kids have, and I want to take the time to point this out. When you look up here, we went ahead and had x squared here and we rewrote it as this. So if you're curious, how come we can't just call this x to the negative 1 and take the integral of it? Okay, so let's think about that. If I take my x and I add 1 to it, negative 1 plus 1 is 0. And then I divide by that new exponent. This gives me something that can't be. I was going to draw an x. That gives me something that can't be. So if I have a singular x, I need to recognize that that came from that natural log function, original function. That ends up being a little bit of a wormhole in mathematics. All right, let's talk about example 6. If I want to find the original function of this rate of change, and I want an equation that's going to help me find the area under the whole curve without any lower or upper boundaries, I'm just going to find the general rule for this indefinite integral. So I'll take it one piece at a time. If I have 6 to the x, I can come up here and recognize that that came from 6 to the x over the natural log of 6. This value, when I go to take the integral of it, is going to give me my natural log of x. And then, of course, my constant. I want to make sure that I remember that if I'm finding my true original function, I'm going to need some x by ordered pair that proves that can help me find what that constant is. All right, so your next task is your homework. So go ahead and spend some time finding these antiderivatives. Come to class with them done so that we can go over them together. All right, after you do this homework, go ahead and check out our next lesson.